Today we're doing the video project for my Calculus 2 class, video project number 1, 3 different integrals for Professor Steve Chow's class, the 4 p.m. one, if anyone cares. And we'll just get right to it. There we go. So, we'll start with integration by parts. And we have not too bad an example here for our integration by parts problem. All we got to do is set up things here. A lot of professors like to use UDV method, but I really like the DI method that I learned from Professor Chow. So we'll just set that up. Some people call a similar thing the tabulature or table method. This one's a little bit better. You can see videos from him about why. Anyway, so we set up our columns here. We got D for what term we're going to derive, and I for what term we're going to integrate. And then we just go work our way down the columns until we get to a better thing than this. So we're going to go ahead and pick our terms, and I pick natural log cosine of x to be my derived term, and the sine of x to be my integrated term, because I don't know how to integrate natural log cosine of x, at least not very well. It's certainly the harder of the two. So now we got to derive this, and it's not too hard. We just have to use the chain rule. Of course, with the chain rule, it's pretty straightforward. We figure out almost right away that we have 1 over cosine of x times the negative sine of x. That's our derivative. Of course, we can rewrite this as the negative tangent of x. And then we're going to go ahead and integrate our sine of x, which is just negative cosine of x. And we see here that this bottom row is something that we could integrate very easily if it was all together in an integral. So we're not going to do any more steps on our DI method table here. We're going to stop here. We're just going to start writing out our answer. So of course, the first part of the answer is just the multiple of these two cells of our table diagonally across the columns. And that will be the negative from here, cosine of x, times the natural log of cosine of x in absolute value bars, because, well, that might be a mistake, but I generally think we can't go wrong when you could have a negative value here. And then, of course, since we've stopped, we need to take the integral of this row, second row, and we need to subtract the integral from our existing term of our answer, just like this. And of course, because these both terms are negative and they're multiplied together, those negatives cancel each other out. They don't cancel this outer one. And tangent can be rewritten. So here we have our first term again, and now we have minus the integral of sine over cosine times cosine. All of them are in terms of x, of course, dx on the end. And we can just cancel these cosines, so now we have a very simple integral. We just have the negative integral of sine. And we already know that integrating sine gets us negative cosine. So, since there's a negative in front, we just have positive cosine. And really, that's it. We're done. Not so bad. Now we have our second problem, which is going to be a trig substitution example. This one's a little bit different from a lot of the ones we did in class, where we only had one constant inside of our square root. Here we have a constant multiple on our x squared. This isn't really a big deal. It just adds a little extra wrinkle. We have to choose our a term for the so-called a term for our trig substitution to be such that it cancels the 4 and replaces it with a 49. And of course, since everything here is a square, we have 7 squared and 2 squared. Then we're just going to have to make a fraction with the square roots of these two numbers in it. theta for our x. So our dx will be 7/2 cosine theta d theta. Once we plug this in, just plugging it directly in and not making any simplifications, we get this lovely beast here. Lovely may be the wrong word. Now right away, of course, we see we have a constant that can come out, and we can write these terms inside the parentheses here as just to well, we can just write them out. They don't have to be inside parentheses because they're just multiples. And we can do a little bit of work. It gets us this. We're just showing every step along the way. 7/2 has come out. We've squared it. 49 over 4 times 4. Of course, the 4's cancel. So we have 49 minus 49 sine squared theta. And, well, we can kind of see what's going to happen next. We have same thing, except we've undone the implied multiplication here. Now we have 49, which is 7 squared, times 1 minus sine squared theta. Because the way square roots work, we can take that constant out. It's going to become 7. Since it's on the denominator, it's going to become 1/7. So these 7s are going to cancel. And we will just have 1/2. And of course, we also know that 1 minus sine squared theta is a trig identity. It's just cosine squared theta. So now we have this, 1/2 the integral of cosine over square root of cosine squared, all theta. That, of course, should be screaming to you, it's just 1. And of course the integral of 1 is just theta in this case. So all of this has just gotten us to theta over 2, or 1/2 theta. But now we have a problem, because our original integral was in terms of x, and we have something here in terms of theta. How do we get from theta to x? Well, we've covered this before. It's pretty easy. We just go back and look at what we've done, and we find that x is 7/2 sine theta, and so 2/7 of x is sine theta, and if we want theta, we just need the inverse sine of 2/7 of x. And so we pop that over here, not forgetting our 1/2 multiple, and we have our answer. We're done with this one. Not so bad. Pretty easy. Finally, we have partial fraction decomposition. And this one is not the hardest, really. In fact, in a lot of the things that are involved in the other ones are harder. It's just involved. There's lots of steps. They're all very easy steps. Most of them are really just write this thing that you already wrote in a different spot. But that doesn't make it not daunting. It is a lot of writing. And we picked one that's doesn't really minimize that at all. We've got here a problem that looks like it could get ugly. But, of course, we always must remember to do our first steps first. They're the easy things you can always do first. We could take this 8 out. I'm not going to. I think it's better left in for this problem. But we can definitely start factoring out our denominator. So, of course, the x squared can come out. Now we have x squared times a quadratic that we can factor. So now we have an x squared and 2 binomials, 3x plus 2 and x plus 1, all in our denominator. And we're ready to start doing our partial fraction decomposition, where we take these multiplied terms and make them denominators of several fractions in a sum. And all we'll need to do is find our constants for the top. And of course, this part here would be, if we'd taken the step to draw it, would be ax plus b over x squared. This is what that one fraction would simplify into 2 fractions. Now, unfortunately, we can't use the cover-up method to find our a. It's not possible. We would have to set x equal to 0, and then this term would be 0. And you can't divide by 0, so we would have no answer. It would be undefined. But there is an a. We'll just have to find it the long way. The rest of them are pretty easy. We'll start with b. Cover-up method, of course. We're going to cover our x squared, knowing that that means that we're going to be using x equals 0 inside this fraction to find our b value, just like so. and it's nice and easy. It comes out to just 4, a nice simple number. Of course, we could have had a 4 here, and then it would be 2. But I like this. And we just proceed doing the same thing. We cover up our next term, and we find that when x is equal to negative 2/3, because that's what would make the term equal 0, that c is 54. There's a little bit of complication here in the denominator where we've got like a compound fraction, I think they call it, where there's a fraction under a fraction. But we just do our math. Negative 2/3 squared becomes 4/9. Negative 2/3 plus 1 becomes a third. You multiply them together, you get 4 over 27, and you multiply the whole thing by 27 over 27, and you get 54. Not bad. D is really easy, in fact. All I do is cover up our term, and we find that D is just negative 8. And as you can see, I've uncovered it here because now we're ready to do the hard part, where we find our A. It's not hard, it's just long, really. It's just lots of writing. Look at all this mess, all these terms. Of course, I did skip a step here. I didn't set this fraction equal to this sum of fractions, even though they are. That's why this works. And I didn't show multiplying the denominator by the sum of fractions and canceling out with all the other denominators. But that's what happened here. So now we have this 8, which is this 8, and all these terms, which are these terms, multiplied by this term. So far, so good. Anyway, this is all just algebra, moving terms around, multiplying, subtracting, using the transitive properties and the associative properties and such like of multiplication, addition, and all that. So we'll just go ahead and collect all of our x terms here into one formula, doing that for each of our coefficients. And we get this. And then we got to distribute our coefficients into their polynomials. That's the word, polynomials. We get this, which is still like so many letters, but it's getting a little better. You can see it's not as long. And then we go ahead and collect up all of our x coefficients and order them by which power of x they go to. And now we have this set up. Right away something jumps out of this. We have an 8 on both sides. This could be simpler. Ys. Now we just have 0 is equal to 2a plus 20. That's the one we're going to go with. We have, of course, 0 x's over here, so that's how we can do that. We also have 0x squared. We could do this one. And we could have 0x cubed. We could do this one. All three of these equals to 0. But this one is just so easy. 2a plus 20 is 0, then a has to be negative 10. And we're ready to go back to the calculus and do our integration. We just plug in all of our terms that we found, our a, b, c, and d, and we have this little beastie here. It's not the most beautiful thing in math, but it works. We go ahead and we take out our constants after splitting it up into multiple integrals, because of course the integral of a sum is equal to the sum of the integrals. That's the same. Now this is the part where you might sometimes trip up if you forget to deal with this constant multiple here. After all, when you're doing integration of 1 over x, well, that's just a natural log of x. But when you're doing 1 over a function of x, like x squared, x plus 2, properly what you're doing, even if you don't write the steps down, is u substitution. And that's why you get this answer and not a 54 here, because, well, if u is 3x plus 2, then du is 3 dx, or du over 3 is equal to x. And once you deal with that 1/3, 54 divided by 3, that's 18. Now we could simplify this further, but I find actually it's not really a simplification. It's more complicated appearing. We could go ahead and make it -2 times everything divided by -2. that doesn't really help. It doesn't look any better, and so I don't do it. We could have taken this minus 2 out right at the beginning and had just 4. All these terms that we found for our A, B, C, and D would have been cut in half. But I don't think it really would have been any better, so I left it in. In fact, we're just going to stop right there, put on our plus C, and we're done with that one. Nice. And that's all of them. You know, just that's all we got here to work with. Now, of course, I just wanted to talk a moment about what I did, how I did this video. Of course, this is just PowerPoint, as you can see up here. Probably, you might be able to see it's actually probably cutting off the screen, but anyway, it's just PowerPoint. And my video software that let me do the bubble and all this other stuff is OBS. And let me show you my desktop. Oh man, OBS is this program here. Everything's stretched because my screen isn't so big, isn't widescreen. But here's OBS. Lets me do things like put my bubble on and blur the background and all that other cool stuff. It even lets me do this for my Zoom videos. And to make all these functions look, these equations look nice inside of PowerPoint, I used MathCast, which is what's a program for creating MathML expressions that look nice. Unfortunately, PowerPoint doesn't let me paste them in as MathML. It doesn't support that, so you might have noticed that some of them were a little blurry because they were pasted in as pictures. But they look pretty good. And yeah, that's it. PowerPoint, MathCast, which is free, and OBS, Open Broadcast Studio, also free. I'll put links in the description. Thanks for watching.